Let's talk about combinations. Here I have 3 stools, and on these 3 stools I've got 5 hats to place down. What I'd like to know is how many groups of hats can be placed on 3 different stools. And when I say group of hats, I could talk about the group ABC. That's really the same group of hats BAC, and it's really the same group of hats BCA. At the end of the day, I have the same 3 hats placed on 3 different stools. So that's what I mean when I say a group of hats. Well, what I want to do to start off is let's just cover up all the hats and just label them as some mysterious unknown hat. I don't really concern myself with which hat is which, just that I have 5 hats. I could place these 3 hats down on stools, or I could place these 3 hats down on stools. It doesn't really matter, but I'm concerned with just the number of ways I can do this. Well, let's take a look and focus on the first stool. Right now I've got 5 different hats that can go on that stool, so there are at this point 5 different ways I can place the first hat on the first stool. Similarly, I can take 4 of the remaining hats and place those on the second stool. So right now, there are a total of 20 possible ways to place the first 2 hats on the first 2 stools. Now, it seems kind of like random that I would just multiply these 2 numbers together. Like, why am I multiplying these? Well, there is a reason why we do this. Let's think about the 5 hats to begin with. Right now, if I had placed any of these hats down, there would be 4 remaining options for the second stool to be placed, for a hat to be placed on the second stool. So for A, if I place hat A first, I could place B, then or C, or D, or E. Those are 4 options there. If I placed hat B first, I could then place hat A, hat C, hat D, hat E. Those could be on the second stool, and so on and so forth. The ends of all of these trees represent all the possible ways I could place 2 hats. There are 20 ends to this tree, so there are 20 possible arrangements. 5 hats times 4 hats gives me 20 possible arrangements. So back to the stools, by extension, I can say that there are 3 ways to place that third remaining hat on the third remaining stool. So this gives me a total of 60 ways to place 3 hats out of 5 possibilities. So what that looks like is here's my second hat placement, and this would look like my tree diagram for all 3 hats being placed down. At the ends of all of these trees are all the different possibilities for placing down these 3 hats out of 5. And you can count them up. There's 60 of them. Quick sidebar on what we're talking about here. When I want to talk about groups of hats, I'm not talking about arrangements. Here's what I mean. Here are 6 arrangements of 3 letters, A, B, and C. There are 6 different ways to arrange them, but there's really only one group of these letters. This all represents the same group or same combination of the letters. It doesn't matter the order that they're in. This is unfortunate because we call a combination lock a combination lock, but it doesn't actually represent combinations. These would all be considered the same combination, 10, 12, 32, or 10, 32, 12, or 12, 10, 32. They're all the same combination of numbers, and so really, technically, a combination lock is something entirely different. These are all considered the same combined numbers. We don't care about the order. All right, end of sidebar. So here are all those combinations of placing 3 hats on 5 hats on 3 stools. And what I want to focus on is one group in particular. Let's focus on the group of hats A and B and C. So here are the 6 different ways that I can place those 3 hats down in the different arrangements. Each group of 3 hats will have 6 arrangements. I chose to look at A, B, and C, but I could have easily selected A, B, and D, or B, C, and E, or B, C, and D. It doesn't matter. But every group of 3 hats will have 6 arrangements. This should make sense since the number of ways to arrange 3 things is 3 factorial, which is 3 times 2 times 1. So what do we do with this? Well, here are all of those different groupings of arrangements for the 60 different ways I can arrange these 5 hats on 3 stools. You'll notice that I have all of the groups A, B, and C in the top left in the blue, all the groups, or all the arrangements of A, B, and D in that light green, and so on and so forth. So why don't we do this? Let's kind of just condense all of these arrangements into their respective groups or combinations. This would be the first group, A, B, and C, the second group, A, B, and D, the third group, A, B, E, and so on and so forth. So in total, when I group all of these arrangements together, there are 10 different combinations or 10 different groups of ways that I can arrange, or rather I can group these 5 hats. So let's generalize this. If I had 5 hats and 3 stools, like I did in this problem, I can multiply 5 times 4 times 3 in order to get the number of arrangements for those 3 stools. If I had 5 hats and 2 stools, I would have one fewer stool to arrange, so I would just find the number of arrangements by multiplying 5 times 4. If I had 6 hats and 2 stools, I could multiply 6 times 5, since I have 6 possibilities for the first stool and 5 possibilities for the second stool. So in general, let's arrange this. Let's go back to the original problem here, and let's look at the number of hats times the number of hats minus 1 times the number of hats minus 2. And I'm going to keep multiplying the number of hats minus the previous, or one less than the previous number, so long as I have stools to work with. Now if you see this hats and hats minus 1, hats minus 2, that kind of looks like a factorial. It's kind of like I have the number of hats factorial. But you'll see in this example, I only multiplied 5 times 4 times 3. So it would be nice if I had some way to cancel out that remaining 2 times 1 that normally hangs out in that factorial notation. Well, it just so happens that I can cancel these out by taking the number of hats minus the number of stools and taking the factorial of that. If you don't believe me, pause the video and work that out on your own. 5 minus 3 is 2, 2 factorial is 2 times 1. So this becomes 5 factorial over 2 factorial. So if n is the number of hats and r is the number of stools, I can generalize this even further to say that n factorial over n minus r factorial gives us the total number of arrangements for 5 hats on 3 stools. So that was a lot to take in. Let's generalize this further. So here I have the expression that gives me the number of arrangements for n number of things for r number of stools. In this case, I had 5 hats, and I could divide 5 factorial by 5 minus 3 factorial, which gave me 60 possible arrangements for ways to place these hats on 3 different stools. This is also called permutations. Next, what I did is I tried to figure out how many different arrangements there were for 3 things, and that's given by r factorial. Since I had 3 stools, I would take 3 factorial to figure out how many ways I can arrange those 3 things. And we kind of condensed that down into just one group or one combination, A, B, and C. And this gave us a 3 factorial number of arrangements, or 6 arrangements. And we want to group those into one combination. So if I take the number of total arrangements and I divide that by the number of arrangements per group, I ended up finding that there were 10 groups in total. So what I'm doing here is I'm taking n factorial divided by n minus 1, or n minus r factorial, and dividing that by r factorial. Or more elegantly, I can put this as n factorial over r factorial times n minus r factorial. And this gives us the number of groups or combinations, or sometimes called choices, with these items. So with 5 hats and with 3 stools, if I choose 3, there are 10 different combinations or groupings for the ways to place these hats. The number of ways to choose r items, if we have n is equal to the number of items and r is equal to the number of choices, taking this away from the hat and stool analogy, I can reuse this formula n factorial over r factorial times n minus r factorial. You might see this also written as n over r, or with these notations as well. And the C in this case stands for combinations. And you might read this as n choose r. So when I say n choose r, that's like thinking I have n hats and I have to choose 3 of them. How many different ways can I do that? So why do we care about this? Why am I going on this combinations tangent? Well, because this is actually going to help us find binomial coefficients. And how we're going to use this, we will see in the next video.